All right. Oh, hang on. Test. Okay, much better. Hey everybody, how's it going? Oh, sorry, it's 6:11. We're just gonna get started here. So today we're just gonna be doing a lot of Green's theorem, or at least as much Green's theorem as we can get done in this section. But yeah, we'll talk about Green's theorem and then we'll end it out. Um, if you're on track and you watched Friday's lecture, we talked about there was flux, a little bit of description of flux. They'll go into a lot more depth in flux on Monday's session with Butler when he talks about surface integrals. So we'll cover a lot of flux probably on Monday's session because most of the flux has to do with surface integrals. We talked about flux through a curve, but we'll get a lot more into that as time goes on. So today we'll just do a lot of Green's theorem. We'll do some Green's theorem practice problems from exams, some exam review sessions, and see how we feel about it. So we talked about Green's theorem. If you guys recall, it was so when we have that little circle on the integral, just like this. Oh, sorry, my computer's freaking out. When we have a integral with a circle on this, when we say c, then we have m dx plus n dy. This circle means that the curve is closed. That's all it means, is that when we have a graph in 3D space, and we have a curve going on, so we have a region here, this region is closed. That's what that circle around the integral means. And you'll see this, we'll get a few different signs on integrals as we get into surface integrals, but this is the first one we start with. And to compute this, you don't have to necessarily compute the line integral. Rather, you can just compute basically the area with a partial n partial y minus partial m partial x dA. So you can take that region, integrate across that area. This is the same thing as like n of y minus m of x, if we're talking maybe in a language that's a little more familiar to us. So we saw that, and we saw this in a problem in lecture. Let C be oriented. C be the oriented curve from 0 to 2 to 0, 2. So if you guys, this is a pretty familiar problem if you guys seen it. Nice little warm up that we got. So we got 0, 0, and then we've got 0, 2. Oh, x would be 0. Sorry. We'd have 0, 2, which would be up here. And then we'd have 2, 2. And it would just look like this. And of course, what it says is it goes from 0, 0 to 2, 2. So it goes that way. And then it goes from 2, 2 to 0, 2. And then it goes back. So of course, orientation is important. Because if we do two different, basically, Green's theorem problems, and we have a region inside of another region and the direction is opposite, kind of like we talked about in lecture with Butler, then you subtract those two different Green's theorem problems. But I haven't seen any of those. We usually have these. Something on exams that's kind of interesting is all the practice exams that I've gone through, there's usually always a Green's theorem problem, and it always kind of looks like a triangle like this. So it's free points if you ask me, but if you can get these Green's theorems problems down, then you definitely have some free points on exams. So no doubt there'll probably be something on however they plan to test you in the future. So when we looked at this problem, of course we want to solve the integral nx minus my dA. This is what we want to solve, and we know that because it's a closed curve. If you see a closed curve, it's going to be a Green's problem. So we have nx, we can look for that. So n is this guy right here, right? That's our n. So if we take the derivative of that with respect to x, it's going to be pretty easy. We just get 1. If we do my, so now we have my. So we take the derivative of that with respect to y, we'll get 3x squared. So now our integral just looks like across the region, 1 minus 3x squared dA. And now for these problems, sometimes you'll get a shape that you might not necessarily be able to. We might have to change it to polar. We might have to change this integral to polar. Or we can just find the area of the shape if our inside is constant. We'll do a couple of those problems. It'll make sense later. But for this problem, we just have to define it like we would any other problem. So we just have our region, and it'd be 1 minus 3x squared. And then we would do dx dy or dy dx. And usually choosing that order is important. But if we do dx dy, we just set up our bounds. So we have to start with a y. Our y is going from 0 to 2. So we'll put 0 to 2. And then our x, maybe I'll use another color. Our x So if we're slicing in the x direction, we're doing this, right? So we go from 0 to this, we go have a slope of 1, so it'd be x is equal to y is that line. So then we go 0 to y. And then we just solve this problem. If you solve the problem, we did it in lecture, you'll get -2. Don't worry, we have plenty of integral problems to solve this session, so we don't have to solve this one. But yeah, are there kind of any questions about Green's theorem like this? I'll open my chat so I can see chat. You guys have any questions? I don't suppose we're doing any quiz problems tonight. Oh, no, I do not have any of the quiz problems prepared. Sorry, no. Unfortunately not. We can do some tomorrow if you want, though. I can. I'll write that down. But we'll do some quiz problems tomorrow. But yes. Okay. Any questions on Green's theorem? All right. Cool. Let's look at a practice problem that you guys could do. It's your turn. All right, your turn. Use Green's problem to solve this question. Finally returns. So if we look at the shape, we can all draw the shape together. 0, 0, and we go to 2, 0. So x is 2, 2, 0. So we go this way, and then we go to 2, 1, which is up here, and then we go back to 0, 0. Perfect. Another triangle problem. We see plenty of these. So let's see how you guys do. Remember, we're just trying to solve for, it's going to be ny minus m, nope, it's going to be nx minus my dA for the region. All right, cool. I'll let you guys solve. You'll need to find nx, you'll need to find my, and see if you can solve that integral. And then you'll have to set up your bounds. I'll set a timer for, let's say, like 4 minutes, and we'll see how you guys do. Good luck. All right, so that was about 4 minutes. Let's see how far you guys got, how well you did. So we have our partial with respect to x and x, and maybe I'll make this nice colors. So we'll do our nx. So this is our, well, let's see. This is our n. So n. So n with respect to x is equal to, it's just going to be cosine times y, 2 minus y. Okay, now let's check our m, which is right here. So our my is equal to, ooh, that's easy, 0. There's no y in there, so it's just going to be 0. Awesome. All right, cool. Easy enough. So let's plug all that into our integral. So we'll have, it's nx minus my, so it'll be cosine of y times 2 minus y. And then we need to do dx dy, or we need to do cosine of y, 2 minus y, dy dx. So we need to do one of those. So we need to set up these bounds. We've done a lot of practice with the setting up the bounds. The one thing we need is this line right here, that red line. So if we look at it, it's basically rising with 1, and the run is 2. So rise over 1 is 1/2. So y is equal to 1/2 x, or x is equal to 2y. One of the two is that line right there. So we care about that because, let's look at it, our y goes from 0 to 1, and our x goes from 0 to 2. So let's start on this left-hand integral and write the bounds for that one first. The x goes from 0 to 2. The y, okay, so we're doing vertical slicing. We start at y is equal to 0, that line, and we go up to y is equal to 1/2 x, so it'll be x over 2. Just to save some room, instead of 1/2 x, it's the same thing. Okay, now let's look at the y, or the right-hand side. So we have, start with dy. Our y is going from 0 to 1, and our x, now we're doing horizontal slicing. So our x goes from 2y to 2. Okay. So now looking at that, I want you to look at that and think which integral we want to solve here. 0 to x over 2 and then 0 to 2, or 0 to 1 and 2y to 2. And there's a few different giveaways that I would say. The first one, I see 2y to 2, and we have a 2y and a 2 and all sorts of stuff inside that cosine, which screams u substitution to me. The other thing is, if we look at the first step when we take this integral, without even taking it, we have to integrate cosine of 2y minus y squared with nothing in front of it. So there's no substitutions that we can do. So I would say this one would be pretty hard to take. So let's try taking the one on the right. So 0 to 1, because it's with respect to x, right? We just put an x in front of the cosine. Okay, dy. Oh, well, I guess I have to write evaluated from. So we evaluate that from 2y to t, dy. So now we just plug in 2 and 2y into the x, like we do for double integrals. So we'll go 0 to 1. And that cosine of the y times 2 minus y isn't going to change. So I'll just save us some of the space. I'm going to write 2 minus 2y times cosine of y times 2 minus y dy, just to save some of the space. But it kind of makes sense to everyone what I did there. We just did the 2 times cosine of y minus the 2y times cosine of y, and then we factored out the 2 minus 2y. Okay, now simplify this a little bit. 0 to 1 of 2 minus 2y times cosine. I know you guys have just been, I just have not been simplifying it, but now it'll be minus y squared. There we go. dy. Okay, pretty simple u substitution, it looks like. We'll use u is equal to 2y minus y squared, and du is equal to 2 minus 2y dy. Perfect, because we have the 2y right there, 2 minus 2y right there, and we have the dy. So that'll just sub to 0 to 1 of cosine of u du, which turns into the sine of u, evaluated from 0 to 1. Ooh, I guess I didn't switch my bounds for u is equal to. So we switch our bounds. We have to do u is equal to, so let's plug in 0. We'll get u is equal to 0. And then for the top bound, we have to plug in 1 to y. And if we do that, we'll get 1. Okay, perfect. So we'll get u is equal to 1. So it actually doesn't change, but it's always important to change your bounds. And then we do that, sine of u, so then we'll get sine of 1 minus sine of 0. Sine of 0 is just 0, so we get sine of 1 as our answer. Sweet. Green's theorem. A little bit of math, 1u substitution, nothing intense. Anybody got any questions about that one? Awesome. All right, cool. We will definitely do another one of these. So, but before we do, we'll do something a little fun. Do this guy. Remember that C now is just that circle with a radius of 1. So don't forget about that. But you'll still need an m of y and an n of x. So you have to solve for that, and then you want to write your integral, n of x minus m of y dA. I'll set another timer for about 3.5, 4 minutes. We'll see how you guys do. Good luck. I believe in you. All right, let's see how you guys did on this one. So I'm guessing you either solved it pretty quick or you've just been stuck at the same place trying to figure out what to do. So hopefully I can help you solve either of those problems. So we're trying to solve this guy. So our my we find, so if we find our my, it's just going to be 3, right? Because we have the 3y in there, and the whole arctan goes away because there's no y in it. Nx is just going to be 7 because this whole thing has a y in it. So we don't care about it. All we care about is the 7, and the derivative of that with respect to x is just 7. So now we write our double integral r of 7 minus 3 dA, which then turns into r of 4 dA, which we could even bring the 4 out of the integral. And you say, okay, that's great. Where do I go from here? So remember, this is just the integral of the area. So it's just all of the little points summed up, and it's just asking for the area of that region. So the area of that region is just equal to pi r squared with a radius of 1. So it'll just be 4 times pi times 1 squared. I'm trying to keep my colors consistent. 4 times pi r squared, which is just equal to 4 pi. Boom. So if you got that right, you probably went head forward into the next problem. Oh, it should 4 pi squared. Sorry, 4 pi squared. Yes. Oh, no. 4. It should be pi r squared. Get my geometry screwed up. There we go. So it should just be 4 pi. There we go. All right, cool. So if you did that correctly, try this guy. It's just about the same one, I bet you. And these were both exam problems. This was fall 19. Oh, I didn't write where this was from. But these were both exam problems. So try this next problem, and you'll hopefully get it pretty quick. You'll just have to draw this guy out. It's just a parallelogram. Find the area of that parallelogram. We'll see how you do. I'll set up another 2-minute timer here, and we'll see you guys do. Good luck. All right, if you're still working, keep working. I'm just going to start graphing this guy really fast, so you guys can keep working if you are, and I'll let you know when I finish graphing. All right, so let's talk about it. So we've got m y is equal to, so we've got the 2x, awesome, there's going to be a 2. There's no y term in the natural log, or no x term in the natural log of y squared plus 1. So it's pretty simple. We get my is equal to 2. Nx is equal to, so this is going to be pretty fun. Okay, so, oh, yeah, sorry. Oh, I'm all turned around. So my, so we got right here. So this is our m term. Did anyone stop me in the chat? Oh, you guys were just letting me go for it. So our m term is the front term, of course. So our m term we got, so we're only looking for a term with y's. There's no term with y. There's no term with y, so it's 5. There we go. And then I got ahead of myself for nx is, the only term with an x in it is that guy. There's no term with an x in the natural log, so it'll be 2. So that our integral will be the region of 2 minus 5 dA, or negative 3 times the area of the region. So if we want to find the area of the region, it's a parallelogram. There are a few ways to do it. I think the easiest way is just to, or I guess it's not a parallelogram. I take that back. It's just some sort of shape. I'd split it into 2 triangles. So there's one triangle. There's the second triangle. The height of our red triangle is, so our final integral would be negative 3 times. Our first triangle is 1/2 times the base, which is 4, because we go from negative 1 to 3. So if we go from negative 1 to 3, we'll get 4 times our height is 0 to 5, 5. And then add that to also the area of 1/2 times the base, which is 4. And then the height is 1. Technically we go down 1, but height is just absolute. All right, now we solve that. We'll get negative 3 times 2 times 5 plus 2 times 1, which is negative 3 times 10 plus 1, negative 3 times 12, or negative 3 times 11, which is negative 33. Did I make a mistake there? Oh, this should be plus, yeah, so it should be 2. 36. Awesome. Is the 1 negative 1? Yes, that's a great question. It is not negative 1 because we're just finding the area of the triangle. So we're just looking for the height of it, which would be technically 1. If it were negative 1, then that means we'd be subtracting from the inside that other triangle. So we want them to both be added. We're just looking for an absolute value of area. Good question. All right, cool. Are there any other questions about these? I mean, these are both exam problems. These are pretty nice. Yeah. All right, cool. Let's do another. So, kind of combining our idea with Green's theorem, writing bounds. We're going to have to write a bound for this one. We can't find the area, sorry. And I would say we use polar coordinates as they give us polar coordinates. So the idea is find your my and your mx or nx, and you have to do that A, carefully because these are a little tricky, but B, because we always just have to do it in Cartesian. And then once we set up our integral, after we set up the my minus, or nx minus my, after we set that up, let's switch the bounds to polar. So first set up the integral, then switch it to polar. I'll set a timer for another 4 minutes here. We'll see you guys how you do. Find these very carefully. Don't forget your chain rule. Chain rule is really important in these. And we'll see how you guys do. When you integrate, you should just have one term in the integral. So there should just be one term. You'll have to use common denominators to get one term. So, all right, good luck. I believe in you guys. All right, so we'll see how you guys did on finding our derivatives here. So let's see, nx, a little tricky. So we have our n is 3 natural log squared, or natural log x squared plus y squared. So our nx will be 3 times, so the derivative, the derivative of the outside first, right? So it'd be 1 over whatever's on the inside, x squared plus y squared. And now we need the derivative of the inside. And remember, we're taking with derivative with respect to x. So if we're doing that, it will be 2x. Yes. My. So now we can kind of see what's going on here. So it'd be, remember, it's 1 over 1 plus whatever that is in the arctan, would be y over x squared. That's derivative of arctangent. And now we need the derivative of the inside with respect to y. The derivative with respect to y would just be 1 over x. Because we have y over x And then if we take the derivative of that with respect to y, the y is what goes away, and it's just 1, and then we still have the over x. A little tricky, but that's what we get. All right, cool. Okay, so now we'll have the integral of nx minus my dA. And if we rewrite that, we'll get, so the nx is first, and I'll combine it with that 2x on the other side. So it'll be 3 times 2, which is 6x, over x squared plus y squared, minus my, which is 1 over 1 plus y squared over x squared, times 1 over x. Okay, so we want to combine these two terms before we switch to polar. And how we could do that is somehow get common denominators. To get common denominators, I need an x squared plus y squared on this side. So to get an x squared plus y squared, and I'll switch colors, I think I will move that x squared on top, if that makes any sense. So I'll put basically everything in terms of x squared, and that will eliminate the x squared in the denominator. And boom, we have an x squared plus y squared on that denominator. And then we still have our 1 over x. That doesn't change. Which then brings us to an, I'll switch back. So then we'll get x over x squared plus y squared. And we'll have a 6x over here over x squared plus y squared minus double integrals. We have a region, dA. And if we combine, then we get 5x. All over x squared plus y squared dA. Sweet. Okay. Our next step is to switch to polar. And we've had a little practice doing this. We're going to get some more right now. So let's write our integrals. We'll have 5x divided by x squared plus y squared dA. And I guess I don't have to rewrite that, but I already did. So there we go. Well, actually, I'm going to run out of room, so I'm going to erase it. You guys can keep it. I'm sure you have more room. Okay, so switch to polar. So remember that, and I'll do it another color. X is equal to r cosine theta. And then x squared plus y squared is equal to r squared. So we can switch out the top for 5r cosine theta and switch out the bottom for r squared. And then we've got our two integrals. And now we need to switch out our dA. Remember that dA is equal to r dr d theta. So then we have r dr d theta. Okay. And now for writing our bounds, they make that pretty easy for us. They just give us it. R is from 1 to 2, and theta is from 0 to pi over 4. So we can just write that. R is from 1 to 2, and from 0 to pi over 4. I think I copied that correctly. Yeah. Awesome. All right, cool. Okay, now we just solve this integral. You can see that we have the r squareds go away, so we just have 0 to pi over 4, 1 to 2 of 5 cosine theta dr d theta. If you've seen, Butler sometimes does this handy little trick where because there's just a theta, there's no r, we can split up these integrals. So it will be 0 to pi over 4 of cosine theta, and there's a 5 out in front, 5 times that, d theta, times the integral from 1 to 2 dr. So if we evaluate this further, we'll just be evaluating sine of theta. Well, we'll have a 5 times everything. I'm always forgetting that. 5 times everything, which is sine of theta, evaluated from 0 to pi over 4, minus, well, plus, or no, times the second integral, which is just r evaluated from 1 to 2. So now we'll get 5 times the sine of pi, so the sine of 0 is 0. So the sine of pi over 4, anyone can think of it, try to recollect it from your unit circle memories. Yes, it is square root of 2 over 2. No one said it, but I could hear you think it. And then our r is just 1, and you can see that pretty easily. So we get 5 over 2, square root of 2. That's our final answer. Some nice polar conversions. Okay, are there any questions on that one? looks tricky, but you can work through it. You can work through it. All right, cool. Okay, my computer will work. There we go. Let's see what's to come. Okay, so we've talked about flux, and you guys remember maybe seeing the equation for flux where it was basically the closed integral, and you have like f dot n ds, and that's also equal to the region div of f dA. And I've seen this in fluid dynamic proofs, and I've seen it in physics 222, if you take physics 222, but I haven't seen this application a lot on calc exams, just because I think it's too easy. It's used more for a constraint on problems than it is actually as an actual problem. And this, of course, is talking about a curve. So like, we talk about a curve, and you can have a flux through that closed surface. But what's more interesting is fluxes through dynamic surfaces. So you can see the surface I have in the image is kind of curved. And if you want a flux of a certain vector flow through that curved surface, we use a different equation. And we need to know about surface integrals to do that. So that'll be talked about on the Monday morning lecture. But you can see that the surface integral, you'll see the equation when it comes along is negative m f of x minus n f of y plus p, which is that third value because now we're in 3 dimensions, dA. And we'll talk about this quite a bit, and we'll do a lot of these problems tomorrow. But yeah, you'll see these on exams. Definitely, I've seen a few of them. But that is the flow through a surface, not necessarily just through a closed line. But yeah, that's just looking ahead. We'll do some of these problems tomorrow, no doubt. It is 6:53, so we finished just a few minutes early. But unless you guys have any questions, that's all I have for today. And our next session is tomorrow at 5:10. Yeah. If there's no questions, are there any questions? Anybody? Awesome. All right, cool. Well, I'll see you guys tomorrow at 5:10. You guys have a nice night. Happy Sunday.